Ladies and gentlemen, let's discuss the different ways by which a continental lithosphere can extend, form rift gravens and eventually break up. There are two main models, the Mackenzie and the Wernicke model, and in addition the delamination and the hybrid model, which are kind of variants of the former two. Here on top we see the pure shear model, the Mackenzie model, which is characterized by a large area of astenospheric upwelling and crustal thinning, where we find bilateral, often listric graben structures with conjugated normal faults on either side of the rift, and typically a very wide rift system. Here in the simple shear and in the delamination and in the hybrid model we see a feature that they have in common, which is a transcrustal or even translithospheric extensional detachment, which means a detachment fault that starts at the surface and underlays the entire rift basin and eventually bends down to meet the bottom of the crust or perhaps even the bottom of the lithosphere. The delamination and the hybrid model are very similar in that regard. The hybrid model has features of both the pure shear Mackenzie and the simple shear Wernicke model. Let's look at the Mackenzie model first. The detachment that we can see is not between an upper plate and a lower plate. That is an important feature of the pure shear model. There is no such subdivision in upper and lower plate, but what we find is an upper crust that is dominated by brittle tectonics and a lower crust that is dominated by ductile tectonics. This is obviously due to the astenospheric upwelling, the thinning of the crust, and the enormous heat input that the entire rift basin experiences. Correlating with the lateral extension, the deformation in the lower crust might be more or less penetrative. An important feature of the pure shear Mackenzie model is that any rift-related volcanism will be found somewhere in the rift basin itself, and we will see in a moment this is different for simple shear dominated models like the Wernicke model. In the Wernicke model we find the separation of an upper plate and a lower plate, as we see here, and the separating boundary is a large detachment starting at the surface, ending at the bottom of the crust or lithosphere. Block rotation is typically unilateral and always synthetic. That means the slip direction along each of these block boundaries that we see here is the same like the slip direction, the displacement direction along the detachment. Half grabens are the typical feature to form, and of course the space generated in the half grabens is usually filled up with young sediments from the rift shoulder or from the topographic high ground of tilted listric blocks. The thinning of the lithosphere is strongest underneath the upper plate's rift shoulder. We see here that at the place where the detachment hits the bottom of the crust and perhaps the bottom of the lithospheric mantle, that is where astenospheric mantle upwelling is strongest. That is also the area where heat input is strongest into the upper plate rift shoulder. Typical for simple shear Wernicke models is volcanic activity that is not in the middle of the rift graben, but rather in the upper plate's rift shoulder. Here we see the delamination model, which is very similar to the Wernicke model. Again, we see the unilateral synthetic shearing forming the listric half graben segments in the main rift basin. But here we now see that there is a long horizontal segment of the detachment underneath the upper plate, and that separates the rift basin from the area where the detachment actually hits the bottom of the crust and where we have the most intense asthenospheric upwelling and accordingly the most intense heat input. In the delamination model, any volcanic activity would be in this area on the upper plate and often quite far removed from the rift basin itself, which might not show any volcanic activity at all. I tend to disagree with the labeling on this image. Strictly speaking, the lower plate is down here underneath the detachment, and the upper plate is all the part on top of it, which would make the listric tilted fall segments technically a part of the upper plate. Also, they are found in the topographically lower rift graben system. The hybrid model, as the name suggests, is a combination of the pure shear and the simple shear model. It has characteristics of both. First here, the unilateral synthetic fault block rotation along synthetic faults, perhaps also a few antithetic faults in the upper plate rift shoulder. And we find a detachment as characteristic for the simple shear models that grades into a wider zone of ductile shearing underneath the upper plate. We also find a wider area of mantle upwelling in this region and accordingly a wider area of asthenospheric heat input. We might find hybrid models in areas where an earlier simple shear model grades and starts to become a pure shear model, and that essentially depends on the rate and the magnitude of heat input into the continental crust. We find hybrid models often in areas where simple shear extension converts into pure shear extension, and that can happen when heat input intensifies. That may be related to the arrival of new plumes along a formerly fairly cold segment of a rift system, or more intensive ascent of hot mantle material in a plume that then distributes and heats up larger areas of the crust. And if that happens, we will get more intense ductile deformation in the lower crust, and that might promote more pure shear characteristics of extension. So the hybrid model might develop in areas where the magnitude of heat inputs varies over time and where we find increasing heat input in specific places that didn't see that before. In this diagram we see a kind of a compilation of different types of continental extension. From left to right we see first segments that are dominated by pure shear or Mackenzie type rifting. Then we see here various types of simple shear rifting, and the different domains are separated by steep falls which we call transfer falls. These falls are essentially strike-slip falls because they accommodate the different magnitude of extension in neighboring segments of the rift. So here in the front we see two segments that apparently are dominated by the typical bilateral extension of pure shear models without a clear detachment. We see here bilateral distribution of listric falls which are top towards us and top away from us on either side of the rift. And that probably also applies here to the second segment. Here is then a major transfer fault, and here we see then the labels upper plate and lower plate, which implies that these segments here are dominated by simple shear type extension. A little bit further on then we find that the position of the upper plate and the lower plate switch compared to the central part of this block diagram, and that would signify that the polarity of extension also changes. Again, transfer faults separate these individual segments. If we would approximately indicate where the lithospheric thinning is most intense, or the stenospheric upwelling is most intense, we probably would find that in the pure shear segments here in the front, somewhere in the middle of the rift basin, we find the most intense crustal thinning. In the simple shear dominated segments, we will find the most intense thinning in the upper plates rift shoulder, for instance somewhere here in this region. And if we switch the polarity and therefore switch the position of the lower and the upper plate, then the area where we have the most intense lithospheric thinning might actually sidestep to the other side of the rift basin, somewhere over here. This sidestepping is important because if our continental rift gravens develop to continental breakup and to the development of mid-oceanic ridges, we find a typical feature that has its origin in these kinds of sidesteppings of intense crustal thinning, and that is the offset of mid-oceanic ridge segments. We know that mid-oceanic ridge segments are connected by transform faults, and these transform faults, they have their initial origin in the transfer faults that separate areas of different styles of crustal extension. We see here an example of the Atlantic, and I have highlighted here some segments of the mid-Atlantic ridge in orange, and we can see that all these segments here are connected with each other along transform faults. Some of them can be hundreds, perhaps even thousands kilometers long. The segments themselves sometimes are very short, sometimes they have a very substantial length along strike. These are the mid-oceanic ridge segments that used to be areas where the continental lithosphere was thinning out most strongly and where the continental lithosphere eventually broke apart. Accordingly, when we look at the topography and the structure of oceanic basins with this typical segmentation and sidestepping of mid-oceanic ridges, we should be aware that initially this geometry was predicted by variable styles of continental rifting and sidestepping of positions where the continental crust broke apart. Let's have a look at two examples of rift gravens as they are described in van der Ploeg and Marschak's textbook. These are the Viking graven, which is between Norway and the Shetland Islands, and the Gulf of Suez, which separates the Sinai Peninsula from mainland Egypt. So two cross sections illustrating features that are now familiar to us. In the Viking graven we see here an older basement which is overlain by Permo-Devonian and Triassic sediments. The basement itself and these earlier sediments up to Triassic age are affected by intense segmentation along normal faults, and these are conjugated normal faults forming horst structures and graben structures. This formed a topography which is overlain by younger sediments, and these younger sediments are essentially Cretaceous and Jurassic, and eventually Paleocene and younger tertiary sediments that form now underneath the shallow sea level in that region. What we can see is that the covering sediments here fill up the topography formed by extensional tectonics, but they themselves are hardly or not affected by the extensional tectonics at all. This gives us a good grip on the timing of the extensional tectonics. It must have happened sometime during or shortly after the Triassic. In the case of the Gulf of Suez, the style is somewhat different. We see essentially half gravens are forming along listric normal fault sets, and we see here the tilting of pre-rift sediments that are covering a Precambrian basement in this case. The pre-rift sediments that we see here, and on top of each of these tilted fault blocks was once a horizontal layer that got tilted during progressive listric normal faulting. And we see wherever there is a breakaway, that means a separation of the hanging wall and the footwall along these listric faults, we find sediments that are called fanglomerate. This is a kind of a combination between fan sediments and conglomerates. That is what this compound means. And these are proximal, very immature sediments that form instantly when topographic steps in the landscapes are created during ongoing extensional tectonics. There are two episodes when these breakaways form. There's here a first breakaway, and we can see here the fanglomerate is then overlain by Miocene salt layers and then by recent sediments. These salt layers are missing here in this area, and from that gap in the stratigraphy we know that this is a later listric normal fault compared to this detachment that we see over here. There is a further complication with a normal fault cutting through the sequence here, but in principle the features from the Gulf of Suez are very similar to the schematic sketches that we saw in the previous video on extensional structures. On the following slides I want to walk you through the evolution of a Red Sea type rift according to Stampfli and Marchand from 1997. You see here a sequence of 6 sketches that illustrate different stages of such a breakup, from more or less intact continental lithosphere to the stage of sea floor spreading that we see here developed in the last sketch. Let's go over each of these stages one by one. Here in the first stage we see transtensional rifting, that means separation, extensional tectonics, perhaps with some strike slip component. This stage may exist a few million years or perhaps tens of million years after the onset of extension, and it could lead up to not much anything, an intracontinental rift system, perhaps that does not develop further, which we call an olacogen or an intracontinental basin, or perhaps it goes to the next phase, to the next stages, and eventually becomes an ocean. In this stage we might find locally intense crustal extension, also basin formation, perhaps even some sort of volcanism, but still at this stage this is not a very large scale or continental scale feature. If the rift basin develops further, perhaps after some 10 million years of time, we will come to the simple shear stage, and the Red Sea developed according to a simple shear, that means Wernicke type style model, and we find here a transection of the lithosphere by a large detachment fault, which eventually will hit the asthenosphere somewhere underneath the upper plate. We find a now well-developed continental graben system that might even be flooded by freshwater or seawater. We see examples for that, for instance, in the East African Rift, where large lakes like Lake Tanganyika or Lake Nyassa are forming. Due to the thinning of the lithosphere here underneath the upper rift shoulder, we will find a decompression of the asthenospheric mantle, and decompression of asthenospheric mantle means decompression melting. These are typically basaltic melts, and these basaltic magmas may reach the surface in the upper rift shoulder and form plateau basalts. The heat input from the asthenosphere will heat up the upper rift shoulder, and that will cause a thermal rise of this region and therefore high topography in the area where we find plateau basalts. Perhaps 20 million years after the onset of crustal extension, we might reach the stage of denudation of the continental mantle, and that is happening here in the lower plate, where the lithospheric mantle actually reaches the surface after the continental crust has been disrupted and separated. So now we have two separated crusts, but we do not yet have a separation of the lithospheres, of the formerly coherent lithosphere. Because here we still see that the upper plate's crust is in contact with the lower plate's lithospheric mantle. A little bit further here underneath the upper plate, we find the main center of heat input, decompression melting taking place, and probably quite active volcanism in this thin wedge of the upper plate. Then we see here an area underneath the upper plate where we have neoformed lithospheric mantle, and that is not because of the generation of new material or new mantle material. This is an effect of cooling, because wherever a stenospheric mantle cools down below about 1280 degrees, it converts into lithosphere. 1280 degrees is a mechanically important temperature. Below this temperature, the material would become significantly harder, its shear strength would increase, and it becomes part of the lithospheric plates, which are mobile on top of the astenosphere and can take part in plate movements such as continental drift. The shelf of the lower plate shows quite significant cooling. We are now here fairly far away from the heat source, which still affects the upper plate shelf, but here we develop subsidence and typically marine transgression. We see here the blue line, the blue shaded areas. These would be probably areas that are underwater, under marine water. To some extent that also affects the upper plate, but here we still have some higher temperature in the crust and therefore some thermal elevation that we have seen on one of the earlier slides. The shelf of the lower plate would develop in a passive continental margin. The tectonics will die out, and the main geological process that can happen in that place is sediment deposition with material from the continent or elsewhere. Some 5 million years later, continental breakup might be complete. We now see here that the formerly coherent lithosphere of one continent has been separated into two separate continents by the formation of new oceanic crust along a mid-oceanic ridge that we see here. We see a fairly substantial amount of neoformed lithospheric mantle underneath the upper plate, and we see that this process also starts to happen adjacent to the lower plate's lithospheric mantle. The shelf of the lower plate will be flooded entirely, and we will see increasing transgression of oceanic water also on the upper plate. Also, we still have some remnant heat here in the upper plate's rift shoulder, which supports thermal elevation. Here we see the aftermath of continental breakup. We see that an increasingly wide ocean is forming along mid-oceanic ridges. We see that both shelves are now flooded due to thermal subsidence that is in response to the cooling of the upper plate. And we see that on either side of the oceans, stable passive margins are forming. Tectonics are dying out, and both of these passive continental margins will be increasingly covered by sediments transported from further inland onto the shelf.